Imagine staring up at the night sky, not just at the familiar stars, but far beyond into the depths where light takes thousands of years just to reach your eyes. Out there, hidden in the vast cosmic ocean, are objects so strange and powerful they defy everything we know about physics. Among them, neutron stars stand as some of the most extreme and enigmatic survivors of the universe's violent drama. These aren't just dead stars, they're cosmic zombies, packing the mass of our entire sun into a city-sized sphere, spinning faster than a blender's blade, and dripping with mysteries we're only beginning to unravel. What if I told you some of these neutron stars are so distant, their light has traveled for millions of years just to whisper their secrets to us? They're the universe's ultimate time capsules, born from the explosions of massive stars, and yet they behave in ways that seem almost impossible. Some pulse like cosmic lighthouses, beaming radiation across space. Others lurk in the darkness, their gravity so intense it warps the very fabric of reality around them. And the strangest part, we've barely scratched the surface of what they can teach us about the forces that shape existence itself. Today, we're diving deep into the heart of this cosmic mystery with 30 mind-bending facts about the universe's most distant neutron stars. From their mind-blowing birth in supernova explosions to the way they bend space and time, each fact is a piece of a puzzle that stretches across the cosmos. You'll discover how these tiny but mighty objects can outshine entire galaxies, why some of them are essentially gigantic atomic nuclei, and what happens when two of them collide in one of the most energetic events since the Big Bang. This isn't just a journey through space, it's a voyage into the extremes of reality where the laws of physics are pushed to their breaking point. So buckle up, because by the time we're done, you'll never look at the night sky the same way again. The birth of a neutron star is a cosmic spectacle unlike any other, a violent, awe-inspiring event that marks the death of one star and the beginning of something far stranger. Picture a star at least 8 times more massive than our sun, burning through its fuel over millions of years. When it finally runs out, the star's core collapses in on itself in a fraction of a second, triggering a supernova explosion so powerful it can outshine an entire galaxy. But the real magic happens in the heart of that chaos. The core doesn't just vanish, it gets crushed by its own gravity into an ultra-dense ball no bigger than a city. That's the moment a neutron star is born. Inside this newborn star, matter is packed so tightly that a single sugar cube's worth would weigh as much as Mount Everest. The force of gravity here is mind-bending, strong enough to flatten atoms themselves, squeezing protons and electrons together until they merge into neutrons. That's why we call them neutron stars. They're not just dense, they're like gigantic atomic nuclei floating in space, defying everything we know about how matter should behave. But here's what's even wilder. When that core collapses, it doesn't just sit there quietly. The star's spin speeds up dramatically, like a figure skater pulling in their arms, except this skater is spinning hundreds of times per second. And because the explosion isn't perfectly symmetrical, some neutron stars get kicked away at unbelievable speeds, racing across the galaxy like cosmic cannonballs. These aren't just relics of a star's death, they're the universe's way of showing us just how extreme physics can get when gravity takes over. If you thought the fastest spinning amusement park rides made you dizzy, neutron stars will blow your mind. These cosmic powerhouses can rotate up to 700 times per second, so fast that their surfaces move at nearly a quarter the speed of light. Just try wrapping your head around that. An object with more mass than our sun, spinning so rapidly it could slice through space like a celestial blender. How does something that extreme even happen? The secret lies in the physics of collapse. When a massive star dies and its core shrinks into a neutron star, it doesn't just get denser, it spins faster, obeying the same law that makes an ice skater twirl quicker as they pull their arms in. Except here, the skater is a collapsing stellar core, and the arms are layers of gas collapsing inward at a significant fraction of light speed. All that angular momentum gets concentrated into a sphere barely 20 kilometers wide, launching it into a hyperactive spin that defies intuition. Among these ultra-fast rotators, pulsars take the spotlight. These neutron stars don't just spin, they beam jets of radiation from their magnetic poles, sweeping across space like interstellar lighthouses. Each rotation sends a pulse of radio waves, X-rays, or gamma rays our way, ticking with a precision that rivals atomic clocks. Some pulsars, like the famous one at the heart of the Crab Nebula, spin 30 times per second, their beams flickering with metronomic regularity. Others, called millisecond pulsars, whip around hundreds of times per second, accelerated by siphoning gas from a companion star. But speed isn't just for show, it has cosmic consequences. The centrifugal force at these extremes flattens the neutron star slightly, making it an oblate spheroid, and if gravity weren't holding it together, the star would fly apart instantly. Yet, against all odds, it holds firm, a testament to physics pushed to its absolute limits. Every pulse, every rotation, is a message from the edge of what's possible, written in the language of space-time itself. Standing on the surface of a neutron star would be like balancing on a cosmic trampoline stretched to its absolute limit, except this one doesn't just bend under your weight, it warps the very fabric of reality. The gravity here isn't just strong, it's 100 billion times more intense than what we experience on Earth. To put that in perspective, if you dropped a marshmallow from just 1 meter above the surface, it would hit the ground at half the speed of light. That's not just falling, that's a full-blown relativistic collision. This crushing gravity does something even more extraordinary. It warps space-time so severely that light itself can't escape in a straight line. Imagine looking at a neutron star from a safe distance. Light from objects behind it doesn't just pass by, it gets bent around the star like water flowing around a boulder in a river. This phenomenon, called gravitational lensing, turns the neutron star into a cosmic magnifying glass, distorting and even multiplying the images of background stars and galaxies. Einstein's theory of relativity predicted this effect, but neutron stars take it to extremes even black holes would respect, and it gets weirder. The star's gravity is so intense that if you could hover near its surface, time itself would slow down for you compared to someone watching from far away. A clock ticking on Earth would race ahead while yours barely moved, like a scene ripped straight from a sci-fi movie, except this is real physics. The very fabric of the universe twists here, offering scientists a natural laboratory to test the limits of Einstein's equations. But perhaps the most mind-bending consequence of all is how this gravity affects the star's own shape. Most celestial objects, like planets or regular stars, are close to spherical because their gravity pulls evenly in all directions. Not a neutron star, its rapid spin flattens it slightly like a cosmic pumpkin, while the unimaginable surface gravity creates a crust so dense it could be riddled with mountains, though these aren't made of rock. There are imperfections in the star's ultra-rigid surface, barely a few millimeters tall, yet containing more mass than the entire Himalayas. Even these tiny bumps warp space-time enough to send ripples through the universe, detectable as gravitational waves when the star spins. This isn't just gravity, it's gravity turned up to 11, twisting the rules of the cosmos into something that feels more like magic than science. And yet, every bizarre effect, every distortion of light and time, is a clue written into the universe itself, waiting for us to decode it. The moment a neutron star is born, it's already hotter than anything in our solar system, including the raging furnace at the heart of the sun. We're talking surface temperatures hitting a staggering 1 million degrees Kelvin, with interiors so scorching they make the sun's 15 million degree core seem almost lukewarm. To put that into perspective, if you could somehow scoop up a teaspoon of neutron star material at birth, it would radiate enough heat to vaporize everything within 1,000 kilometers instantly. That's not just hot, it's a temperature so extreme it redefines the very meaning of the word. But here's what's even more mind-boggling. All that heat isn't coming from nuclear fusion like in ordinary stars. Instead, it's trapped energy from the star's violent collapse, a remnant of the supernova explosion that birthed it. Imagine taking an entire star's worth of thermal energy and compressing it into an object smaller than Manhattan. That's the kind of concentrated fury we're dealing with. And unlike the sun, which steadily burns hydrogen for billions of years, a neutron star has no fuel left to burn. It's a cosmic ember glowing white-hot purely from the energy of its own creation. Yet even these unimaginable temperatures don't last forever. Over time, neutron stars gradually cool, shedding their heat into the void of space. The first 1,000 years are the most dramatic, with surface temperatures dropping by half as the star radiates away its birth fire. But the cooling slows to a crawl after that, stretching across billions of years. Some of the oldest known neutron stars still hover around 100,000 degrees hotter than the sun's surface, but a far cry from their initial inferno. What's fascinating is how they cool. Unlike regular stars which lose heat through light and solar wind, neutron stars rely on two bizarre processes: neutrino emission and photon radiation. Deep inside, protons and electrons are squeezed so tightly they merge into neutrons, releasing a flood of ghostly neutrinos that carry away energy like invisible thieves. Meanwhile, the surface glows in X-rays and gamma rays, invisible to our eyes but detectable by telescopes tuned to the universe's most violent wavelength. And then there are the exceptions: neutron stars that refuse to cool. Ones tangled in magnetic fields so intense they generate heat through friction, or those feeding on material from a companion star, reigniting their surfaces like cosmic blast furnaces. These outliers remind us that even in death, stars find ways to defy expectations, turning the cold equations of physics into a spectacle of lingering fire. If you thought the gravity of a neutron star was extreme, wait until you hear about its magnetic field, especially when it belongs to a magnetar. These aren't just strong magnets, they're cosmic monsters with fields so powerful they can distort the very structure of matter itself. Picture this: Earth's magnetic field is strong enough to guide compass needles, but a magnetar's field is 1,000,000,000,000 times more intense. That's not just stronger, it's a force so unimaginable it exists on a scale where physics textbooks start to sweat. At these extremes, the magnetic field does something downright terrifying. It rips atoms apart. Under normal conditions, atoms are stable, with electrons orbiting nuclei in neat little shells. But near a magnetar, the field is so strong it warps those orbits into thin, needle-like shapes before shredding them completely. The electrons get torn away, and what's left isn't even recognizable as matter in any conventional sense. It's more like a soup of subatomic particles, forced into alignment by a magnetic grip that could pluck a credit card from your pocket from halfway across the solar system. Now imagine that kind of power trapped inside a spinning, ultra-dense star. The tension builds until crack. The star's rigid crust snaps under the strain. These aren't earthquakes, they're starquakes, seismic events so violent they release more energy in a millisecond than our sun does in 100,000 years. When a magnetar's crust fractures, it unleashes a burst of gamma rays and X-rays bright enough to outshine every star in the Milky Way combined. In 2004, a magnetar 50,000 light-years away flared so powerfully it temporarily ionized Earth's upper atmosphere, all from halfway across the galaxy. What's even wilder is how these magnetic fields form in the first place. When a neutron star is born from a supernova, the chaotic collapse can amplify its magnetic field to ludicrous levels, especially if the original star was already highly magnetized. But magnetars take it further, with fields so intense they shouldn't even be stable. Theory suggests they might decay within 10,000 years, yet we've spotted magnetars much older, meaning something somehow is keeping these cosmic monsters alive far longer than the rules say they should be. And then there's the ultimate question. What happens if you get too close? The answer is as brutal as it is fascinating. A human body would be torn apart long before reaching the surface, not just by gravity, but by the magnetic field twisting every molecule into oblivion. Even from a safe distance, a magnetar's flares could sterilize planets light years away. These aren't just stars, they're cosmic disasters waiting to happen. And yet, they're also some of the universe's most brilliant laboratories, pushing the laws of physics to their breaking point and daring us to understand them. Even the most precise cosmic clocks sometimes stutter, and when they do, it reveals secrets hidden beneath a neutron star's impenetrable surface. Pulsars, those hyperactive lighthouses of the universe, usually spin with such unwavering rhythm that their pulses could set your watch. But occasionally, without warning, one will suddenly speed up its rotation in a fraction of a second before settling back into place. Astronomers call these events glitches, and they're like cosmic hiccups that betray the storm raging beneath the star's calm exterior. What could possibly make a celestial object weighing more than our sun abruptly spin faster? The leading theory points to the neutron star's superfluid core, a bizarre state of matter that flows without friction. Picture a mug of coffee spinning endlessly because nothing slows it down. Now imagine that coffee is a quantum soup of neutrons swirling inside a star at nearly light speed. When the star's rigid outer crust slows slightly due to magnetic braking, this superfluid doesn't get the memo. It keeps spinning at its original pace, storing energy like a wound-up spring. Then, in a sudden snap, it transfers that pent-up motion to the crust, causing the entire star to lurch forward in a glitch. But there's another contender: crust quakes. Neutron star surfaces aren't perfectly smooth. They're under unimaginable strain from gravity and magnetic fields. Occasionally, the crust fractures like a tectonic plate, causing the star to contract slightly. Just like that figure skater pulling in their arms, this tiny shrinkage makes the star spin faster to conserve angular momentum. Some glitches might even be a chaotic mix of both phenomena, with superfluid vortices unlocking while the crust shudders under pressure. The real magic lies in what these glitches reveal. Each one is like a sonogram of the star's interior, offering clues about densities and states of matter we could never recreate on Earth. When the Vela pulsar, one of the most active glitches, speeds up roughly every 3 years, it's practically handing scientists a roadmap to its core. By studying how much energy is released and how quickly the star recovers, researchers can estimate the thickness of the crust, the viscosity of the superfluid, and even the strength of quantum bonds between particles. And sometimes glitches defy all expectations. In 2016, a pulsar in the constellation Gemini spun up so violently that it didn't just hiccup, it practically coughed, with its rotation rate jumping by a staggering 0.000045 seconds. That might sound minuscule, but for an object that precise, it's like a metronome suddenly doubling its tempo. Events like these suggest there's still so much we don't understand about the turbulent dance between a neutron star's layers. These cosmic anomalies remind us that even the most predictable objects in the universe hold surprises. Every glitch is a crack in the facade, a fleeting glimpse into the heart of a star where matter exists in forms beyond our wildest imagination. And with each one, we inch closer to answering the ultimate question: what really happens inside nature's most extreme pressure cooker? The idea of mountains on a neutron star sounds like something from a science fiction novel, until you realize these aren't the towering peaks we know on Earth. Imagine the Himalayas crushed down to the height of a pencil tip, and you're close to grasping the bizarre reality of neutron star topography. These so-called mountains are mere millimeters tall, yet they weigh more than entire mountain ranges on our planet. How does something so tiny hold such unimaginable mass? The answer lies in the star's crushing gravity and a crust unlike anything in our solar system. When a neutron star forms, its outer layer cools into a rigid shell, but it's far from flawless. intense magnetic fields, rapid rotation, and the mind-bending pressure of gravity create microscopic imperfections, wrinkles in the fabric of space-time itself. These deformations are so slight they'd be invisible to the naked eye, but their impact is colossal. A 1-centimeter mountain on a neutron star contains more mass than Mount Everest because every atom here is packed 100 trillion times tighter than steel. The crust isn't just solid, it's a crystalline lattice of atomic nuclei squeezed into a near-perfect arrangement, withstanding stresses that would vaporize any known material. What's even wilder is how these mountains move. As the star spins, the crust flexes like a frozen ocean under tidal forces, generating ripples in space-time called gravitational waves. In 2017, scientists detected these waves from colliding neutron stars, but even solitary stars emit faint whispers as their surfaces shift. Each tremor, each minuscule shudder, carries clues about the star's internal structure, hinting at the superfluid vortices swirling beneath the crust or the quantum oddities locked inside. But here's the real kicker: these mountains aren't permanent. Over millennia, the star's gravity fights to smooth out every bump, flattening the crust with relentless force. It's a cosmic tug-of-war between rigidity and gravity, where even the slightest irregularity becomes a battleground. Some neutron stars might sport glacial flows not of ice, but of ultra-dense matter creeping sluggishly under pressure, eroding mountains atom by atom. Others could suddenly fracture, unleashing starquakes that rewrite their topography in an instant. These minuscule mountains are more than curiosities. They're portals into the extreme physics governing neutron stars. By studying them, we're not just mapping alien landscapes, we're decoding the universe's most unforgiving laboratory, where matter exists in states beyond our wildest experiments. And every tiny peak, every imperfection, is a testament to the fact that even in the most hostile corners of the cosmos, nothing is ever perfectly smooth. Deep in the violent chaos of a neutron star collision, something extraordinary happens. The universe itself becomes a cosmic alchemist. When two of these ultra-dense remnants spiral into each other, they don't just merge, they unleash a firestorm powerful enough to forge the heaviest elements in existence. That gold ring on your finger, the platinum in a catalytic converter, they weren't made in the heart of a star like carbon or iron. They were born in the fury of a kilonova, a flash of light so brilliant it outshines entire galaxies for days. The process starts with a dance of doom. As two neutron stars circle each other, losing energy through gravitational waves, their fate is sealed. In the final moments, they rip each other apart, spewing chunks of neutron-rich material into space at nearly light speed. This isn't just debris, it's a superheated soup of atomic nuclei bombarded by a maelstrom of free neutrons. In this extreme environment, something called the rapid neutron capture process, or R process, kicks in. Atomic nuclei greedily snatch up neutrons faster than they can decay, bulking up into heavyweight elements like gold, platinum, and even uranium. A single merger can produce hundreds of Earth masses worth of these precious metals, scattering them across interstellar space like cosmic treasure. The proof came in 2017 when humanity witnessed this phenomenon for the first time. Gravitational wave detectors LIGO and Virgo caught the ripples from a collision 130 million light-years away, while telescopes around the world swiveled to catch the afterglow. The data was staggering. A kilonova's light curve matched predictions of heavy element production perfectly, with spectra revealing telltale signatures of strontium, gold, and other R-process elements. For astronomers, it was like finding the smoking gun of cosmic chemistry, a direct link between neutron star mergers and the stuff that makes up our jewelry, electronics, and even parts of our own bodies. But here's what's even more mind-blowing. These collisions might be the universe's primary gold mines. Before 2017, scientists debated where heavy elements came from, supernova. Rare stellar flares, the kilonova discovery tilted the scales dramatically. Calculations now suggest a single neutron star merger can seed a galaxy with enough precious metals to account for all the gold and platinum we've ever found. That means the very atoms in your watch or wedding band might have once been part of a cataclysmic crash between two dead stars billions of years ago. Yet kilonovae aren't just element factories, they're also laboratories for extreme physics. The aftermath of a merger can birth a black hole, a hypermassive neutron star, or even a magnetar with a magnetic field strong enough to strip atoms apart from light years away. Some theories suggest these events might be the source of mysterious fast radio bursts, or that their debris disks could spawn planets made entirely of solid gold worlds where rain would literally be worth its weight in precious metals. Every neutron star collision is a reminder that the universe doesn't just create life, it also minted the very materials that make modern civilization possible. The gold in your phone, the platinum in a lab coat, the uranium fueling reactors, all of them were born in the most violent crucibles imaginable, proving that sometimes destruction is the mother of creation. Some neutron stars don't journey through the cosmos alone. They're locked in a gravitational tango with other cosmic heavyweights, creating some of the most energetic duos in the universe. Picture a neutron star paired with a giant star, siphoning gas from its companion like a celestial vampire. As material spirals onto the neutron star's surface, it heats up to millions of degrees, erupting in X-rays so intense they can outshine entire star systems. These binary partnerships aren't just fascinating to watch, they're cosmic clocks, their orbits ticking ever closer to a cataclysmic finale. One of the most dramatic examples is the X-ray binary, where the neutron star's gravity strips away layers of its companion, forming an accretion disk of superheated plasma. The stolen gas doesn't just pile up quietly, it's funneled by magnetic fields onto the neutron star's poles, triggering thermonuclear explosions called bursts. In milliseconds, these flashes can release more energy than our sun does in a week, lighting up the X-ray sky like cosmic fireworks. Some systems, like Scorpius X1, blaze so brightly they're considered the X-ray equivalents of quasars, visible across interstellar distances. But sometimes the companion isn't another star, it's a black hole. These pairings are rare, but when they occur, the dynamics become even wilder. The black hole's immense gravity distorts space around the neutron star, tugging it into an erratic orbit. Over time, the two spiral inward, their dance emitting gravitational waves that ripple through space-time. When they finally collide, the merger unleashes a kilonova, a flash of light and heavy elements that seeds the galaxy with gold and platinum. The most famous example of this fate is the system Pulsar J07373039, where two neutron stars orbit each other every 2.5 hours. Einstein's theory predicts their inevitable doom. As they lose energy to gravitational waves, their orbits will shrink until they collide in about 85 million years. When LIGO detected gravitational waves from a similar merger in 2017, it confirmed what theorists had long suspected. These binaries are the universe's ultimate time bombs, ticking toward explosions that forge the building blocks of planets and life itself. Yet not all companions survive the relationship intact. In some cases, the neutron star's intense radiation and particle winds slowly evaporate its partner, leaving behind a ghostly stellar corpse. Others might fling their companions into interstellar space, creating runaway stars hurtling through the galaxy. And in the rarest scenarios, a neutron star's gravitational kick during its birth can send both stars careening apart, turning a once close duo into lonely drifters. These binary systems are more than just cosmic oddities, they're laboratories for studying gravity, matter, and the extremes of physics. Every X-ray flare, every orbital wobble, tells a story about how matter behaves under conditions we could never recreate on Earth. And when two neutron stars finally embrace in a collision, They don't just vanish, they rewrite the cosmic ledger, scattering the elements of life across the void and proving that even in death, stars never truly dance alone. Even among neutron stars, cosmic oddities that defy imagination are RxJ 1856.5-3754 stands out. This solitary wanderer, floating just 400 light-years from Earth, holds the title of the closest known neutron star to our solar system. But don't let its relative proximity fool you. This isn't some friendly neighbor dropping by for a cosmic chat. RxJ 1856 is a ghostly relic, drifting through space without the usual trappings of its kind. No pulsar beams, no swirling nebula, not even a companion star. It's just an eerily smooth sphere of ultra-dense matter, glowing faintly in X-rays as it quietly cools in the void. What makes this neutron star so special isn't just its distance, it's what's missing. Most neutron stars are shrouded in the wreckage of their supernova births or surrounded by magnetized particle clouds. But RxJ 1856 is what astronomers call a bare neutron star, stripped down to its essentials like a cosmic skeleton. Without the distraction of surrounding debris, scientists can study its surface properties with unprecedented clarity, almost like examining a single, perfectly polished gem under a microscope. And what they've found is bizarre even by neutron star standards. Observations from telescopes like Chandra and XMM Newton reveal that its surface temperature is a scorching 700,000 degrees, yet it emits almost no visible light, only high-energy X-rays. That's because its gravity is so intense, it bends light back toward the surface, making the star appear smaller and dimmer than it really is. If you could see it with the naked eye, it wouldn't even twinkle. It would be a featureless, almost imperceptible dot, colder looking than the faintest star in the sky. Then there's the mystery of its motion. Unlike most neutron stars, which rocket through space at breakneck speeds after their violent births, RxJ 1856 is moving relatively slowly, just enough to leave a faint trail in interstellar gas. Tracing its path backward suggests it originated from a star cluster in the Scorpius-Centaurus association, but the details of its supernova explosion remain elusive. No remnant, no shockwaves, just a quiet, almost apologetic exit from stellar life. But perhaps the most intriguing question is why it's so alone. Did its supernova blast its companion star into oblivion? Or was it born in isolation, a solitary giant that collapsed without fanfare? Whatever the case, this neutron star serves as a cosmic control experiment, letting astronomers test theories about heat distribution, magnetic fields, and even the nature of matter itself, free from the noise of more chaotic environments. It's a reminder that sometimes the universe's greatest secrets aren't hiding in the brightest explosions or the most violent collisions, but in the silent, solitary objects drifting right under our noses. Neutron stars might seem eternal, their super-dense cores defying the ravages of time, but even these cosmic titans have an expiration date. Their fate hinges on two brutal truths: gravity always wins in the end, and the universe has a way of turning the most extreme objects into something even more extreme. Picture a neutron star lingering in the darkness, its spin gradually slowing as it radiates away energy. Over trillions of years, it would cool into a black, inert sphere, a black dwarf made of degenerate matter, so cold it barely emits a whisper of heat. But that's the peaceful ending. The far more dramatic demise happens when a neutron star crosses a critical threshold, either by gorging on stolen matter or merging with another dense object, and transforms into the universe's ultimate abyss, a black hole. Take accretion, the cosmic equivalent of overeating. If a neutron star orbits a companion star and siphons off too much gas, the added mass can push it over the edge. The star's gravity, already unimaginably strong, grows until even neutron degeneracy pressure, the quantum force that keeps it from collapsing further, can't hold back the crush. In a split second, the star implodes, vanishing behind an event horizon. The transition isn't always clean. Some neutron stars might oscillate violently, shedding mass in bursts before finally succumbing, while others could collapse silently, as if the universe itself hit a mute button. Then there's the merger scenario, where two neutron stars spiral together in a death spiral. For a fleeting moment, their combined mass forms a hyper-dense object, a neutron star so massive it shouldn't exist. Theory suggests this overstuffed remnant might teeter on the brink for milliseconds, its core oscillating between collapse and resistance before gravity decisively wins the tug of war. The resulting black hole swallows not just the stars but also the surrounding space-time, sending ripples across the cosmos as gravitational waves. But here's the haunting twist: not all neutron stars get a dramatic exit. Isolated ones, far from any source of extra mass, might never cross the critical limit. Instead, they'll slowly bleed away their spin and heat over timescales longer than the current age of the universe, fading into darkness like embers in a cold fireplace. Quantum mechanics even suggests their protons could decay, eroding them particle by particle until nothing remains. Whether by gluttony, collision, or slow decay, every neutron star's story ends the same way, with gravity having the final word. And in their death throes, they gift the universe something extraordinary: black holes that warp space-time, elements that seed new stars, and proof that even the mightiest objects must eventually yield to the laws of physics. Their endings aren't just finales, they're the universe's way of recycling extremes into new wonders. Deep inside a neutron star's core, where gravity crushes matter beyond recognition, the rules of physics as we know them might be breaking down entirely. While the star's outer layers are made of neutrons packed tighter than sardines in a can, the very center could be something far stranger, a soup of free-floating quarks, hyperons, or even matter that doesn't exist anywhere else in the universe. Picture squeezing an atomic nucleus until it bursts, its protons and neutrons dissolving into their fundamental building blocks. That's the kind of pressure we're talking about here, so intense it could be tearing apart the very fabric of reality. The leading theory suggests that under these conditions, neutrons themselves might not survive. Instead, they could melt into a plasma of up, down, and strange quarks, the particles that usually stay locked inside protons and neutrons. This hypothetical quark matter would behave unlike anything we've ever seen. A fluid with near-perfect superconductivity, where electric current flows without resistance and heat moves so efficiently it defies earthly physics. Some models even predict a crystalline arrangement of quarks, forming patterns so dense they'd make diamond look like tissue paper. The catch: we have no way to recreate these conditions on Earth. The Large Hadron Collider can smash particles at incredible speeds, but it can't sustain the crushing, sustained pressure of a neutron star's core. Then there's the wild card: strange matter. A controversial idea proposes that under extreme enough pressure, ordinary matter could transform into a new state where strange quarks, a heavier, unstable cousin of up and down quarks, dominate. This strange matter would be eerily stable, potentially more so than the atoms making up our bodies. If it exists, a single droplet could, in theory, convert anything it touches into more strange matter, a cosmic chain reaction turning planets or even stars into bizarre quark globs. Thankfully, observations haven't found evidence of this apocalyptic scenario, but the possibility lingers like a shadow at the edge of physics. What makes this mystery so tantalizing is that neutron stars are essentially cosmic laboratories, testing matter under conditions we'll never replicate. Every glitch in a pulsar's spin, every gravitational wave from a merger, carries clues about what's happening in those impenetrable cores. Recent data from collisions detected by LIGO hinted that neutron stars might be slightly squishier than expected, possibly due to exotic cores softening their internal structure. Meanwhile, X-ray telescopes measuring star sizes suggest some might be too small to fit traditional neutron-only models, hinting at something even denser inside. The truth is, we're still grasping in the dark. until we can peer inside a neutron star, perhaps by decoding their gravitational wave fingerprints or catching a whiff of quark matter in a kilonova's aftermath. This remains one of the universe's most tantalizing unsolved puzzles. It's a reminder that even the most extreme objects in the cosmos still guard secrets, waiting for the right moment to reveal how matter behaves when pushed to its absolute limits. If you could somehow hover near a neutron star and look sideways at it, you might witness one of the universe's most breathtaking optical illusions, light itself bending into perfect rings around the star like a cosmic halo. This isn't science fiction, it's Einstein's general relativity in action. The star's immense gravity warps the fabric of space-time so severely that light from distant stars or galaxies passing behind it doesn't travel in a straight line. Instead, it curves around the neutron star like water flowing around a rock, creating a phenomenon called gravitational lensing. But here's where it gets surreal. When the alignment is just right, that warped light doesn't just bend, it loops into a complete circle known as an Einstein ring. These rings aren't just beautiful curiosities, they're cosmic measuring tapes. By studying the size and distortion of the ring, astronomers can calculate the neutron star's mass with astonishing precision. The larger the ring, the more massive the star, because greater mass warps space-time more dramatically. It's like weighing an object by seeing how much it dimples a stretched bedsheet, except here, the bedsheet is the fabric of the universe itself, and the object is a city-sized star heavier than our sun. One of the most striking examples occurred in 2021, when the Hubble Space Telescope spotted an Einstein ring around a neutron star in the constellation Ursa Major. The ring's near-perfect symmetry revealed the star's mass to be about 1.4 times that of our Sun, matching predictions almost exactly, but the real magic lies in the details. Tiny imperfections in the ring, slight brightenings or asymmetries, can hint at unexpected features, like an uneven distribution of mass beneath the star's surface, or the presence of an otherwise invisible companion object tugging on it gravitationally. What's even wilder is that this effect isn't unique to neutron stars. Black holes and entire galaxies can create Einstein rings too. But neutron stars offer a Goldilocks zone for study. Their gravity is strong enough to bend light dramatically, yet they're compact enough that the rings form at scales telescopes can resolve. With black holes, the ring often forms too close to the event horizon to observe clearly, while galaxy-scale lensing tends to be messier, distorted by clumps of dark matter and interstellar gas. These luminous rings are more than just pretty pictures. They're proof that gravity doesn't just pull, it sculpts. Every time we spot one, we're glimpsing the invisible hand of space-time itself, twisted into shapes that reveal the secrets of the universe's most extreme objects. And with next-generation telescopes like the James Webb Space Telescope and the upcoming Vera Rubin Observatory, we're on the verge of catching even more of these cosmic mirages, each one a gateway to understanding the true nature of matter, gravity, and the fabric of reality. At first glance, the surface of a neutron star seems like a barren wasteland, gravity so strong it flattens atoms, heat so intense it vaporizes anything ordinary. But look closer and you'll find something unexpected, an atmosphere. Not the thick, swirling blankets of gas that shroud planets or stars, but a whisper-thin layer barely a few centimeters deep, clinging to the surface like a wisp of smoke. This isn't just any atmosphere, it's a seething, ultra-dense film of hydrogen or helium, compressed by gravity to densities rivaling Earth's oceans. And despite its minuscule thickness, it holds the key to some of the most violent X-ray fireworks in the universe. How does an atmosphere survive in such a hostile place? The answer lies in the neutron star's monstrous gravity, which traps even the lightest elements like an invisible cage. Hydrogen or helium atoms, remnants of the star's pre-supernova life or stolen from a companion, get pressed into this razor-thin layer. But here's where physics gets strange. The atmosphere isn't uniform. Gravity sorts it like a cosmic centrifuge, with heavier elements sinking to the bottom while lighter ones float atop, creating a bizarre onion skin effect on an atomic scale. What's truly astonishing is how this delicate skin shapes the star's deadly radiation. When X-rays from the star's scorching surface blast upward, they slam into the atmosphere's atoms, getting absorbed and re-emitted in a frenzied dance. This interaction doesn't just soften the X-rays, it imprints them with a chemical fingerprint, altering their energy spectrum in ways telescopes like Chandra can decode. Some neutron stars even sport hotspots at their magnetic poles, where the atmosphere gets superheated to millions of degrees, funneling X-rays into beams so intense they punch through interstellar space like cosmic searchlights. But these atmospheres are fragile. A passing interstellar cloud or a flare from the star's magnetic field can strip them away in an instant, leaving the surface bare. Others might be replenished by gas siphoned from a nearby companion star, creating a cycle of destruction and rebirth. And in Magnetars, the magnetic field is so ferocious it can lock the atmosphere in place, forcing it to vibrate like a drumhead and producing X-ray echoes that reveal the star's inner structure. This delicate balance between annihilation and persistence makes neutron star atmospheres cosmic gold mines for physicists. By studying how they filter and distort X-rays, scientists can map surface temperatures, measure magnetic fields, and even probe the star's crust beneath. It's a reminder that even in the most extreme corners of the universe, the tiniest details, like a few centimeters of gas, can hold the answers to the biggest questions. In the cosmic graveyard of dead stars, Pulsar J0108-1431 stands out as a grizzled elder, a neutron star that's been spinning quietly in the darkness for roughly 200 million years. That makes it one of the oldest neutron stars ever discovered, a relic from a time when dinosaurs still roamed Earth. Unlike its younger, hyperactive cousins, this ancient pulsar has slowed to a leisurely rotation once every 2.6 seconds, its beams of radio waves flickering like a fading lighthouse in a distant ocean. What's fascinating about this old timer isn't just its age, it's how it defies expectations. Most neutron stars cool rapidly after their violent births, but Pulsar J0108 has managed to cling to a faint glow, emitting X-rays and thermal radiation that hint at an internal heat source we don't fully understand. Some theories suggest its crust might be unusually thick, trapping warmth like a cosmic thermos. Others propose residual magnetic friction or even the slow decay of superfluid vortices in its core could be keeping it slightly toastier than predicted. Then there's its motion, or rather, its lack of drama. While many neutron stars rocket through space at hundreds of kilometers per second, this one drifts relatively slowly, as if conserving energy for its twilight years. Tracing its path backward suggests it was born in a region now empty of massive stars, a ghost from a stellar family long since scattered. Yet for all its quietude, Pulsar J0108 is a goldmine for astronomers. Its slow spin and faint emissions offer a rare glimpse into the late-stage evolution of neutron stars, what happens when the fireworks fade and these cosmic engines begin to wind down. By studying its subtle pulses and temperature, scientists can test theories about how neutron stars cool over time, how their magnetic fields decay, and even how often they collide with interstellar material during their epic journeys. This ancient pulsar is more than just a curiosity, it's a time capsule from an era when the universe was younger, and its whispers across the electromagnetic spectrum are teaching us what happens when a neutron star grows old. In its quiet persistence, it reminds us that even the most violent objects in the cosmos eventually settle into stillness, their stories written in the slow fade of radiation and spin. When a neutron star's crust cracks under unimaginable pressure, it doesn't just shudder silently, it rings like a colossal cosmic bell. These starquakes, some releasing more energy than 1 billion atomic bombs, send vibrations racing through the star at nearly half the speed of light. The entire city-sized sphere begins oscillating in distinct patterns, with standing waves bouncing between its surface and core like sound echoing through a cathedral. What makes this phenomenon extraordinary isn't just the scale, but how we detect it. The vibrating star actually modulates its X-ray emissions, creating a celestial fingerprint that reveals secrets about its internal structure. X-ray telescopes like NASA have caught these vibrations in action. When a magnetar experiences a starquake, its superheated surface begins pulsating at precise frequencies, some as high as several hundred hertz. These aren't random tremors, they're harmonics, specific tones that depend entirely on the star's density and composition. Picture striking a wine glass and hearing its characteristic ping, then realizing you could calculate the glass's thickness and material just from that sound. That's exactly what astrophysicists do with neutron stars, using their X-ray echoes to probe regions we could never otherwise observe. The most famous example came in 2004, when the Magnetar SGR 0600-20 unleashed a starquake so powerful its vibrations lasted nearly 10 minutes. ESA's XMM Newton telescope recorded the oscillations as minute fluctuations in X-ray brightness, revealing the star's crust to be far stiffer than predicted, likely due to a bizarre nuclear posture phase where matter arranges itself into sheets and tubes under extreme pressure. Other observations show some neutron stars vibrating in multiple modes simultaneously, like a bell being struck at different points, allowing scientists to create three-dimensional maps of their interiors. What's truly fascinating is how these echoes decay. On Earth, a bell's ringing fades quickly due to air resistance and internal friction. But in a neutron star, where gravity binds everything unimaginably tight, vibrations can persist for astonishing durations. Some modes dampen within seconds, hinting at a viscous superfluid core, while others linger, suggesting crystalline layers in the crust. By studying these differences, researchers have even estimated the thickness of neutron star crusts, about 1 kilometer of ultra-dense matter, which sounds thin until you realize it contains nearly half the star's mass. These cosmic echoes are more than just stellar seismology. They're direct messages from the edge of physics, showing us how matter behaves when crushed beyond recognition. Every quake, every vibration, is a chance to test whether our theories about quantum forces and nuclear interactions hold up under the universe's most extreme conditions. And with next-generation X-ray telescopes coming online, we're on the verge of hearing neutron stars ring with even greater clarity, turning their ghostly echoes into a symphony of discovery. Some neutron stars don't just hurtle through space, they graffiti it. Take the pulsar known as PSRB 2224+65, tearing through the cosmos at over 800 kilometers per second. Behind it stretches a glowing tail of energized particles, a cosmic wake so striking astronomers nicknamed it the Guitar Nebula. From our vantage point, the pulsar sits where the guitar's neck meets its body, with a curving, luminous trail resembling strings. Except these strings are charged particles blasted outward by the star's fierce wind, illuminating interstellar gas like a neon sign in the void. These tails aren't just pretty accidents, they're physical records of a neutron star's journey. Like comets streaking past the sun, pulsars shed material as they plow through space, but the comparison ends there. A comet's tail is fluffy ice and dust pushed gently by solar radiation. A neutron star's tail is a high-energy particle jet, forged by its ridiculous speed and brutal magnetic field. The Guitar Nebula's strings, for instance, glow in X-rays and radio waves, energized by electrons spiraling along magnetic field lines at nearly light speed. What's wild is how these tails reveal secrets the star itself might hide. By studying the curve and intensity of a tail, astronomers can trace a pulsar's path back to its birth, often a supernova explosion that kicked it into motion like a cosmic cannonball. Some tails even flicker or flare unexpectedly, hinting at turbulence in the interstellar medium or sudden releases of trapped particles. The mouse pulsar, another speed demon, sports a tail that kinks sharply, suggesting it's plowing through a dense patch of gas like a boat hitting rough water. But the real magic happens when these tails interact with their surroundings. In 2019, astronomers spotted a pulsar with a tail so long it stretched 130 light-years, the longest ever seen. As the tail rams into surrounding gas, it creates shock waves that heat the material, triggering bursts of gamma rays and X-rays. These collisions are like cosmic particle accelerators, natural laboratories where matter gets hurled around at energies we could never achieve on Earth. From a distance, these glowing trails might look like delicate brushstrokes on the universe's canvas, but up close, they're evidence of a neutron star's relentless momentum, its magnetic fury, and its ability to turn even the emptiest corners of space into a spectacle of light and motion. Every tail is a story written in particles and radiation about where these cosmic bullets came from and where they're headed next. Every pulsar in the universe is essentially a cosmic clock, and the way it ticks reveals its age with astonishing precision. Just like a spinning top gradually slowing on a table, these neutron stars lose rotational energy over time, their furious spins decaying at a rate that leaves forensic clues about their birth. Scientists call this slowdown the breaking index, a number that captures how rapidly a pulsar's rotation is bleeding energy into space through magnetic fields and particle winds. The higher the breaking index, the faster the star is hitting the cosmic brakes, and the more accurately we can rewind its history to pinpoint when it first exploded into existence. Take the Crab pulsar, a celestial celebrity born from a supernova so bright it was recorded by Chinese astronomers in the year 1054. Today, it spins 30 times per second, but it wasn't always this sedate. By measuring its current spin rate and how quickly it's decelerating, astronomers have calculated it must have originally whirled at nearly 60 rotations per second when it first formed. That means in just under 1,000 years, it's lost half its rotational speed, a slowdown so consistent it's become the gold standard for aging other pulsars. The math behind this is elegant. A pulsar's age equals its current spin period divided by twice its slowdown rate. For the Crab pulsar, that works out to roughly 1,200 years, uncannily close to the actual observed date of its supernova. But not all pulsars play by the same rules. Some, especially those with off-axis magnetic fields, slow down more erratically, while recycled millisecond pulsars barely slow at all, their spins artificially prolonged by stolen stellar material. What's fascinating is how these breaking indices expose a neutron star's hidden environment. A higher-than-expected slowdown might hint at an invisible debris field dragging on the star, while an unusually low one could suggest a magnetic field decaying faster than predicted. The Vela pulsar, for instance, has a breaking index slightly below 3, implying its magnetic axis is wobbling like a top about to fall, a detail we'd never know without tracking its spin over decades. These spinning timekeepers are more than just relics, they're active witnesses to stellar evolution. By cataloging pulsar ages across the galaxy, astronomers have reconstructed timelines of star formation, identified ancient supernova remnants, and even spotted outliers that defy expectations like Pulsar J0586, a pulsar calculated to be over 250 million years old yet still spinning once every 4 seconds. Whether meticulously regular or stubbornly erratic, every pulsar's spin is a story waiting to be decoded, written in the universal language of motion and time. The spin of a neutron star doesn't just ripple the fabric of space-time, it actively drags it along like cosmic molasses. This mind-bending phenomenon, known as frame dragging, occurs when a massive rotating object literally twists the surrounding space-time continuum around itself. Picture dropping a spinning marble into a vat of honey. As the marble turns, it pulls the thick syrup into a swirling motion around it. Now replace the marble with a neutron star and the honey with the very fabric of reality, and you've got frame dragging on a galactic scale. Einstein's theory of general relativity predicted this effect over a century ago, but neutron stars take it to extremes. Their rapid rotation, some whirling hundreds of times per second, combined with their immense gravity, creates a vortex in space-time so pronounced it could alter the orbit of a passing asteroid or even bend light in spirals around the star. The closer you get to the surface, the more dramatic the drag becomes, like stepping into a whirlpool where the currents grow fiercer toward the center. NASA Gravity Probe B mission, launched in 2004, provided some of the most compelling evidence for frame dragging, though not around a neutron star. The satellite measured the effect around Earth, detecting how our planet's rotation subtly warps space-time. The results matched Einstein's predictions to within 1%, proving the phenomenon is real. But if Earth's gentle spin can twist space-time, imagine the havoc a neutron star wreaks. Some pulsars exhibit slight timing irregularities in their beams that can't be explained by magnetic fields alone. Hints that frame dragging might be subtly altering the path of their radiation as it escapes the star's gravitational grip. What's truly astonishing is how this effect scales. A neutron star's frame dragging is so powerful that if you could hover near its surface, space-time itself would be dragged around at a significant fraction of the speed of light. Falling into orbit around one wouldn't be a simple elliptical path. You'd spiral in a corkscrew motion, helplessly caught in the star's space-time whirlpool. Even binary systems containing neutron stars show traces of this. Their orbits slowly decay not just from gravitational waves, but from the relentless tug of each star's rotational energy on the surrounding cosmic grid. Frame dragging isn't just a curious side effect, it's a fundamental feature of how mass and motion sculpt the universe. Every spinning neutron star is a reminder that space isn't just an empty stage where matter performs. It's an active participant, twisted and stretched by the sheer force of these cosmic dynamos. And as we detect more of these stars, especially ones in tight binary orbits, we're getting closer to measuring frame dragging in its most extreme form, where the universe itself becomes a fluid, bending to the will of the densest objects it contains. Some neutron stars aren't just cosmic loners, they're celestial predators, slowly devouring their stellar companions in a lethal dance of radiation and gravity. Meet the Black Widow pulsars, named after the spiders notorious for consuming their mates. These neutron stars don't just orbit their partners, they blast them with particle winds and X-rays so intense they're literally boiling them away into space. PSRB 1957+20, the original Black Widow pulsar discovered in 1988, is a textbook example of this astrophysical predation. Locked in a tight orbit with a small, lightweight companion, likely the charred remnant of what was once a sun-like star, this pulsar whips around every 9 hours, bombarding its partner with high-energy radiation. The effects are catastrophic. The companion star's outer layers are superheated to tens of thousands of degrees, creating a glowing cloud of vaporized gas that trails behind it like a cosmic comet tail. But here's where it gets even more brutal. The pulsar's relativistic particle winds carve through this gas, stripping away material at a rate that will eventually leave nothing behind. Astronomers estimate the companion is losing the equivalent of Jupiter's mass every billion years, a death by 1,000 cuts on a cosmic scale. What makes black widows so fascinating isn't just their destructive tendencies, it's how they warp their environment. The pulsar's radiation pressure creates a shock wave where its particle winds collide with the companion's evaporating atmosphere, heating the gas to X-ray emitting temperatures. This interaction also eclipses the pulsar's radio waves periodically, as the dense cloud of ablated material passes between us and the spinning neutron star. It's like watching a murder mystery unfold in real time, with the victim's remains obscuring the killer's flashing beacon. But the story doesn't end there. Some black widows, like Pulsar J1311-3430, have companions so small and lightweight, less than 1% the Sun's mass, that they're more akin to oversized planets than stars. These redback pulsars, named after another species of cannibalistic spider, suggest a later stage in this grim process where the companion has been whittled down to a planetary core. Others, like Pulsar J2241-5236, have already vaporized their partners entirely, leaving behind only a disk of debris, a cosmic crime scene with no victim left to mourn. These deadly duos are more than just celestial oddities, they're natural laboratories for studying extreme physics. By measuring how quickly the companions evaporate, astronomers can calculate the pulsar's wind intensity, magnetic field strength, and even the efficiency of mass stripping in binary systems. And because black widows are often discovered through their eclipsing behavior, they offer a unique way to find otherwise hidden neutron stars lurking in the shadows of their own destruction. Yet the most haunting question remains: what happens when the feast ends? Simulations suggest that once the companion star is fully evaporated, the pulsar's spin will gradually slow, its beams fading into obscurity. But the material it's torn away won't just vanish, it'll enrich the surrounding interstellar medium with heavy elements, seeding future generations of stars and planets. Even in annihilation, these black widows contribute to the cycle of cosmic life, proving that in the universe, death is never just an end, it's the beginning of something new. The Crab Nebula isn't just a beautiful cloud of gas, it's a cosmic light show powered by the furious energy of a neutron star at its heart. Like a lighthouse beam cutting through fog, the Crab Pulsar's relentless radiation illuminates the nebula's twisting filaments, energizing them to glow across the electromagnetic spectrum from radio waves to gamma rays. This isn't passive starlight, it's an ongoing particle storm where electrons spiraling along magnetic fields at nearly light speed emit synchrotron radiation, painting the nebula in ethereal blues and purples visible from thousands of light years away. What makes this interaction so spectacular is the sheer efficiency of the energy transfer. The pulsar loses rotational energy as it spins down, converting it into high-energy particles that flood outward like a cosmic fire hose. These particles collide with the nebula's slower-moving gas, heating it to millions of degrees and causing it to fluoresce like neon under ultraviolet light. The result is a dynamic, ever-changing structure where new tendrils and shockwaves form continuously, a celestial canvas being repainted in real time. But the Crab Nebula is far from unique. Across the galaxy, similar pulsar wind nebulae act as natural particle accelerators, their intricate shapes revealing the complex interplay between neutron star winds and interstellar debris. The Vela pulsar, for instance, powers a nebula with delicate tendrils resembling jellyfish tentacles, while MSH-15-52, one of the most energetic pulsar nebulae known, flaunts X-ray jets stretching dozens of light years. Each structure tells a story about its central engine's power and the environment it's carving through. Perhaps most remarkably, these nebulae serve as cosmic batteries, storing energy that can persist for millennia after the original supernova fades. The Crab's glow isn't just leftover explosion debris, it's actively replenished by the pulsar's output, making it shine 30 times brighter than the sun would in its place. This ongoing illumination allows astronomers to study not just the neutron star itself, but how its energy transforms entire regions of space, turning what could have been a fading ember into one of the sky's most enduring masterpieces. Beneath the crushing gravity of a neutron star lies one of the strangest solid surfaces in the universe, a crust so dense it could withstand stresses that would vaporize diamonds. Picture a layer just 1 kilometer thick, yet containing half the star's mass, where atomic nuclei are packed into a crystalline lattice so tight it resembles a cosmic neutron prison. These aren't ordinary atoms like those in Earth's crust. Gravity here has compressed matter so severely that atomic nuclei press shoulder to shoulder, submerged in a swirling ocean of free electrons. The result is a material with strength beyond any earthly metal, 10 billion times stronger than steel. This crust isn't just dense, it's structured in ways that defy conventional physics. At the surface, the pressure is relatively mild, about 100 billion times Earth's atmospheric pressure, allowing nuclei to retain some semblance of their identity. But descend just a few meters, and the squeeze becomes so intense that nuclei deform into bizarre shapes. Rods, slabs, and even hollow tubes scientists whimsically call nuclear pasta. These formations aren't static. They're constantly under strain from the star's ferocious magnetic fields and rapid rotation, creating microscopic cracks and imperfections that occasionally trigger starquakes. The crust's rigidity is what makes these quakes possible. When magnetic stresses build or the star's spin adjusts, the crust fractures like a pane of glass under torsion, except these fractures release more energy than a magnitude 23 earthquake. Some of these events, like the one observed from SGR 1806-20 in 2004, fling out bursts of gamma rays detectable across interstellar space. Yet despite these violent episodes, the crust remains intact, its nuclear bonds unbroken. That resilience comes from the same property that makes it so strong: the Coulomb repulsion between atomic nuclei, reinforced by degenerate electron pressure, creates a near unbreakable barrier against collapse. What's truly mind-bending is how this crust interacts with the star's interior. Below about half a kilometer, the nuclei dissolve into a neutron superfluid, a state where matter flows without friction. The boundary between crust and core isn't sharp, but a gradual transition where matter loses its crystalline order and becomes quantum soup. This interface is where some of the star's most puzzling behaviors originate, like the sudden spin-up glitches in pulsars, where the superfluid's vortices unlock and transfer angular momentum to the crust. Compared to Earth's geology, neutron star crusts are more like neutron-rich ceramics than rocky layers. Their incredible strength means they can support mountains, tiny imperfections mere millimeters high, yet weighing more than terrestrial mountain ranges. These minuscule bumps warp spacetime enough to emit gravitational waves, and when the star rotates, they create ripples in the fabric of reality itself. This crust isn't just a shell, it's a dynamic, ultra-dense armor protecting the star's exotic interior while shaping its observable behavior. Every crack, every tremor, every magnetic shift leaves an imprint on the star's radiation, offering clues about conditions we can't replicate in any lab. It's a reminder that even in the most extreme corners of the cosmos, matter finds ways to organize, and sometimes that organization is as rigid as the universe allows. Deep inside a neutron star's core, where gravity crushes matter beyond recognition, neutrons might not just sit still, they could be flowing in a bizarre quantum dance. Scientists suspect these ultra-dense stellar remnants harbor something extraordinary, a superfluid, not the kind you'd find in a lab on Earth, but an ocean of neutrons moving without a hint of friction, as if the universe itself forgot to apply the brakes. This isn't just theoretical speculation. It could explain two of the most puzzling behaviors of neutron stars: their sudden spin-up glitches and their unexpectedly rapid cooling. Imagine a liquid so slippery it could whirl around a bowl forever without slowing down. That's the essence of a superfluid, a state of matter where particles sync up in perfect harmony, eliminating all internal resistance. In a neutron star's core, pressures are so extreme that neutrons normally bound in atomic nuclei break free and form this exotic quantum soup. Here, they behave less like individual particles and more like a single, coordinated wave, sliding past obstacles with effortless grace. This superfluid isn't confined to a tiny pocket. It might fill the inner kilometer of the star, swirling beneath a rigid crust like a hidden cosmic whirlpool. The proof of this surreal phenomenon lies in those mysterious glitches, sudden speed-ups in a pulsar's spin. Picture a figure skater tucking their arms to spin faster, except in this case the skater is a city-sized star and the arms are vortices in the superfluid. Ordinarily, the star's crust slows down over time as it radiates energy, but the superfluid beneath it, unaffected by friction, keeps spinning at its original pace. When these vortices suddenly unlock and transfer their momentum to the crust, the entire star lurches forward in a fraction of a second. The Vela pulsar, famous for its frequent glitches, practically serves as a laboratory for this effect, with each hiccup offering clues about the superfluid's properties deep inside. But the superfluid's influence doesn't stop there. It also acts as the star's built-in cooling system. Normally, a neutron star's incredible density would trap heat for eons, but superfluidity changes the game. When neutrons pair up in this quantum state, they release energy in the form of neutrinos, ghostly particles that zip straight through the star, carrying away heat like invisible thieves. This process can cool a young neutron star from 1,000,000 degrees to a mere 100,000 in just a few centuries, far faster than traditional models predict. Observations of unexpectedly cool neutron stars, like the one in the Cassiopeia, a supernova remnant, fit neatly with this theory, as if the universe left behind a cosmic fingerprint pointing directly to superfluid activity. Yet the full picture remains elusive. Some theories suggest protons in the core might form their own superfluid, coexisting with the neutron sea to create a dual-phase quantum realm. Others propose that magnetic fields could tangle the superfluid into knots, creating localized turbulence that occasionally flares up in bursts of X-rays. The only way to test these ideas is to keep watching neutron stars glitch by glitch, neutrino by neutrino, as they whisper their secrets across the light years. Every anomaly in their spin, every flicker in their cooling rate, is a puzzle piece waiting to slot into place, revealing what happens when matter is pushed to the edge of physics itself. Hidden beneath the chaotic surface of a neutron star, something extraordinary is happening. An entire celestial body is vibrating like a struck gong, sending ripples through the very fabric of space-time itself. These aren't just random tremors, they're precise harmonic oscillations, some ringing at frequencies hundreds of times per second, creating gravitational waves that propagate across the universe like cosmic sound waves. When a neutron star's crust cracks during a starquake or its core undergoes a sudden shift, the entire star rings at specific tones dictated by its density and internal structure, tones so pure they could theoretically be converted into actual sound if we had the right instruments to hear them. Gravitational wave observatories like LIGO and Virgo are designed to catch these faint whispers from the cosmos. Unlike electromagnetic waves which travel through space, gravitational waves are ripples in space-time itself, distortions caused by massive accelerating objects. Picture dropping a pebble into a pond and watching the concentric waves spread outward. Now imagine that pond is the three-dimensional grid of reality, and the pebble is a neutron star quivering after a catastrophic crust fracture. These waves squeeze and stretch space as they pass, altering the distance between objects by fractions of an atomic width, an effect so minuscule it requires lasers and mirrors suspended in vacuum chambers to detect. What makes these oscillations so valuable to science is how they encode the star's deepest secrets. Just as a bell's pitch reveals its shape and material, a neutron star's vibrational modes, dubbed starquakes, when large enough, betray details about its interior that light alone cannot. Some modes ripple through the crust like seismic waves, while others dive deep into the core, probing the possible superfluid regions where matter flows without friction. The frequencies of these oscillations depend critically on the star's mass, radius, and internal composition, making them a Rosetta Stone for deciphering the equation of state of ultra-dense matter. But here's where it gets even more fascinating. These gravitational waves aren't just scientific data. they are echoes of events that, if converted into sound, might resemble eerie cosmic music. Simulations suggest the vibrations of a neutron star would produce tones akin to a deep, resonant hum, with overtones layered like a choir of dissonant bells. Some theorists have even mapped hypothetical frequencies into audible ranges, revealing patterns that shift as the stars spin and magnetic field evolve. It's a haunting reminder that the universe isn't silent. It's a symphony of vibrations, most of which lie far beyond human hearing. The challenge lies in detection. While LIGO has famously spotted gravitational waves from colliding black holes and neutron stars, catching the subtler waves from a lone neutron star's oscillations is like trying to hear a whisper in a hurricane. Current observatories aren't quite sensitive enough to pick up these faint, continuous signals, but next-generation detectors, like the proposed Einstein telescope or space-based LISA, could change that. With improved sensitivity, scientists might soon tune into the universe's background hum, listening for the distinctive songs of vibrating neutron stars as they echo through the void. These cosmic vibrations are more than just curiosities. They're a direct line to understanding matter under conditions impossible to replicate on Earth. Every oscillation, every ripple in space-time carries a message from the heart of a neutron star, written in the language of gravity itself. And as our detectors grow more advanced, we're not just observing the universe anymore, we're learning to listen to it. Tens of thousands of light-years from Earth, far beyond the familiar spiral arms of the Milky Way, spins Pulsar J1748-2446 AD, one of the most distant neutron stars ever detected. This cosmic loner drifts through the galaxy's halo, a sparse outer region where stars are few and far between, its radio pulses taking nearly 30,000 years just to reach our telescopes. To put that into perspective, when this pulsar's light began its journey toward Earth, humanity was still in the Ice Age, hunting mammoths with stone tools. The sheer distance isn't just a number, it's a time machine offering a glimpse into the universe's past while testing the limits of our technology. Studying these far-flung neutron stars is like trying to spot a lighthouse through thick fog. Their faint signals must travel unimaginable distances, battling interference from interstellar gas, magnetic fields, and the cosmic background hum before arriving as whispers in our detectors. Even the most powerful radio telescopes, like Arecibo before its collapse or the sprawling arrays of the Very Large Array, strain to pick up these pulses amidst the noise. Pulsar J1748 signal is so stretched and weakened by its journey that without sophisticated signal processing algorithms that sift through terabytes of data for repeating patterns, it would vanish into the cosmic static. But distance isn't the only obstacle. Neutron stars in the halo often move at breakneck speeds, a legacy of the asymmetrical supernova kicks that birthed them. Their high velocity, combined with the Milky Way's gravitational pull, sends them careening through regions where the interstellar medium is patchy and unpredictable. As their beams pass through varying densities of gas and plasma, the signals scatter and distort, an effect astronomers call dispersion measure. Correcting for this requires meticulous calibration, like tuning a radio dial through a storm of interference just to catch a fleeting, distorted voice. Yet the effort pays off. These distant pulsars are cosmic trail markers, helping map the Milky Way's mysterious halo, a region devoid of bright stars but teeming with dark matter. By timing their pulses with nanosecond precision, astronomers can triangulate their positions and velocities, tracing paths that reveal the galaxy's gravitational field in unprecedented detail. Some, like Pulsar J1748, even serve as tests for Einstein's general relativity, their pulses arriving with delays that expose how space-time itself curves over vast distances. But perhaps the most intriguing aspect of these faraway relics is what they suggest about neutron star populations. If we're finding them in the halo where stellar densities are low, how many more might be lurking in the voids between galaxies? Their presence hints at a hidden diaspora of stellar corpses ejected during the Milky Way's violent youth, now drifting unseen through the darkness. Every distant pulsar we uncover is a reminder that the universe's most extreme objects aren't confined to familiar neighborhoods. They're out there, in the deep, spinning silently and waiting for their stories to be heard. Some neutron stars don't journey through the cosmos alone. They're born dancing with a partner in a gravitational waltz that could last billions of years. The Hulse-Taylor binary, discovered in 1974, gave us our first glimpse of this cosmic pas de deux. Two neutron stars separated by just a few solar diameters, orbiting each other every 7.75 hours. What made this pair extraordinary wasn't just their closeness. It was how they precisely confirmed Einstein's prediction that such systems should lose energy by emitting gravitational waves. Every year, their orbit shrinks by about 3.5 meters as ripples in space-time carry away momentum, an observation so precise it earned the Nobel Prize in 1993. These binary systems form when two massive stars already orbiting each other both explode as supernova. If the explosions don't kick the stars apart, the resulting neutron stars continue their orbital embrace. Some, like Pulsar J0737-3039, orbit so close they could fit between Earth and the Moon, their deadly dance accelerating with each passing millennium. The gravitational forces at play here are staggering. Tidal distortions stretch each star slightly, creating bulges that constantly shift as they whirl around each other at fractions of light speed. But such tight orbits come with an expiration date. As gravitational waves bleed away energy, the stars spiral inexorably inward. The final moments of this dance are among the most violent events in the universe. When the two neutron stars finally collide, their combined mass often exceeds the threshold for neutron star stability, collapsing instantly into a black hole. The merger unleashes a kilonova explosion, a flash of light 1,000,000 times brighter than our sun, while spewing out enough heavy elements like gold and platinum to seed entire galaxies. The Hulse-Taylor system has about 300 million years left before its fatal embrace. But in cosmic terms, that's barely the blink of an eye, a fleeting moment before these stellar remnants rewrite the laws of physics one final time. At the heart of an aging neutron star, something extraordinary is happening: a cosmic deep freeze, transforming its seething core into the universe's hardest diamond. Over billions of years, as these stellar remnants shed their birth heat, their interiors may undergo a phase change more dramatic than water turning to ice, a transition from seething nuclear fluid to crystalline solid. Imagine matter so densely packed that atomic nuclei, normally separated by vast emptiness, are pressed shoulder to shoulder in a rigid lattice, their structures locked in place by pressures 100 billion times greater than Earth's core. This isn't just solidification, it's matter surrendering to gravity's ultimate triumph. The process begins with the star's crust, where nuclei already exist in bizarre, phases, sheets, rods, and tubes of nuclear matter shaped by competing forces. As temperatures plunge below 10 million degrees, quantum mechanics takes over, organizing these deformed nuclei into an orderly crystalline structure resembling a cosmic metal, albeit one with protons and neutrons standing in for atoms. But the real transformation happens deeper, in the inner crust and core, where densities exceed atomic nuclei by orders of magnitude. Theoretical models suggest free neutrons, normally slippery as superfluid, may likewise crystallize, forming a neutron solid interlaced with superconducting protons. The result, a celestial matryoshka doll with layered solid phases, each denser than the last. This freezing process isn't just academic, it rewrites the star's magnetic playbook. Younger neutron stars generate magnetic fields through dynamo action, their churning interiors acting like cosmic generators. but as the core solidifies, that dynamo stalls. Charged particles lose mobility, freezing magnetic field lines into the crystalline structure like artifacts in amber. Observations of ancient pulsars support this. Their magnetic fields decay slower than predicted, as if preserved in astrophysical refrigeration. Some magnetars, with their inexplicably persistent fields, might owe their longevity to partially frozen interiors locking magnetism in place against time's erosion. Spin tells another tale of stellar glaciation. A crystallized core alters how angular momentum transfers between the star's layers. Without a frictionless superfluid to mediate glitches, older neutron stars rotate with metronomic consistency, their spins as steady as atomic clocks. The absence of dramatic speed-ups in millisecond pulsars like Pulsar J2144-3933 hints at this transition. Their precise ticks suggest interiors that have crossed the quantum threshold into solidity. Yet even here, mysteries linger. Some isolated pulsars show tiny, irregular timing variations, perhaps the last shudders of freezing superfluid vortices deep within, fighting crystallization's grip. The ultimate fate of these frozen giants remains an open question. Given enough time, trillions of years, far longer than the current age of the universe, a neutron star might cool into an inert black dwarf, its heat and light extinguished, its spin halted, its frozen core a relic of quantum forces pushed to their breaking point. But until then, each crystallizing neutron star serves as a time capsule, preserving extremes of physics we can only dream of replicating. Their gradual solidification isn't an ending, it's a new chapter in the life cycle of matter, written in the language of quantum crystals and magnetic fossils. Long before telescopes spotted their telltale pulses across the cosmos, neutron stars existed as scribbles in a notebook, a stroke of theoretical genius decades ahead of their discovery. In 1934, astronomers Walter Baade and Fritz Zwicky proposed something radical: that the violent death throes of massive stars could leave behind unimaginably dense cores composed entirely of neutrons. At the time, the very concept seemed ripped from science fiction. The neutron itself had only been discovered 2 years earlier, and the idea of squeezing an entire sun's worth of mass into a sphere smaller than Manhattan defied all intuition about how matter should behave. Baade and Zwicky's paper was astonishingly prescient. They didn't just predict the existence of neutron stars, they correctly linked them to supernova explosions, estimating their density at 10 to the 14th grams per cubic centimeter, a number later proven almost spot on, and even suggested these objects might power cosmic rays. Yet for decades, their hypothesis gathered dust. Without observational evidence, most physicists dismissed neutron stars as mathematical curiosities until the night of November 28, 1967, when graduate student Jocelyn Bell Burnell noticed an anomaly in her radio telescope data from Cambridge. The signal was unlike anything seen before, sharp, rhythmic pulses arriving every 1.337 seconds with atomic clock precision. Bell and her advisor Anthony Hoyle initially labeled it LGM1, short for Little Green Men, because the regularity seemed almost artificial. But as more of these pulsating sources were found across the sky, the truth became clear: these weren't alien transmissions, but the spinning beacons of Baade and Zwicky's long-predicted neutron stars. The first discovered pulsar, later named CP19-1921, was emitting radio waves from its magnetic poles as it rotated, sweeping beams across Earth like a cosmic lighthouse. What's remarkable isn't just that theorists foresaw neutron stars, it's how accurately they guessed their extreme properties without a single example to study. Zwicky's notes even speculated about their rapid spins and strong magnetic fields, features that would take decades to confirm. The delay between prediction and discovery wasn't due to flawed science but technological limits. Detecting these faint, city-sized objects required advances in radio astronomy that simply didn't exist in the 1930s. By the time Bell's telescope caught that first pulse, neutron stars had already spent 33 years hiding in plain sight, not in the stars but in the pages of forgotten journals. This story holds a profound lesson about how science unfolds. Sometimes the universe's greatest secrets aren't uncovered through observation alone, but through the power of imagination, of daring to extrapolate physical laws to their most extreme conclusions. Baade and Zwicky's neutron stars joined a proud tradition of theoretical predictions, from Neptune's existence inferred from Uranus' wobbly orbit to black holes emerging from Einstein's equations decades before Cygnus X1 offered proof. In each case, mathematics acted as a time machine, revealing truths about the cosmos long before technology could catch up. Today, as we study pulsars blinking at the edge of black holes or neutron stars colliding in kilonova explosions, we're witnessing the culmination of a dialogue between theory and observation that began with a handful of equations scribbled nearly a century ago. It's a reminder that some of the universe's most exotic creatures don't always announce themselves with fanfare. Sometimes they whisper first to those who dare to dream with numbers. Some neutron stars don't just spin alone in the void, they've somehow gathered planets around them, cosmic survivors clinging to the most inhospitable homes imaginable. Take Pulsar B1257+12, a pulsar nearly 2,000 light-years away that hosts at least 3 rocky worlds, each bearing silent witness to the violent chaos that created them. These aren't the gentle, dust-formed planets of young star systems, they're orphans of catastrophe, born from the ashes of a supernova so powerful it should have vaporized everything in its vicinity. That they exist at all rewrites the playbook on how planets come to be. The story begins with death. When a massive star goes supernova, the explosion unleashes enough energy to outshine entire galaxies, blasting its outer layers into space at 10% the speed of light. Conventional wisdom said nothing could survive this apocalypse, yet somehow, around Pulsar B1257+12, a disk of debris persisted. Maybe the supernova was lopsided, leaving a portion of the star's corpse shrouded in cooling gas. Or perhaps the pulsar's intense radiation and particle winds later gathered interstellar material, forging new worlds from the cosmic wreckage. Whatever the case, the result was a protoplanetary disk unlike any other, a swirling maelstrom of heavy elements, superheated to millions of degrees and threaded with deadly radiation. Against all odds, planets coalesced here, not gas giants, but dense, rocky bodies with masses comparable to Earth's. The innermost world, Poltergeist, is a charred cinder racing around its pulsar every 25 days, while its siblings, Phobter and Draugr, follow wider orbits. Their surfaces, if they have any, would be unrecognizable, bombarded by gamma rays and bathed in magnetic fields strong enough to strip molecules apart. There's no atmosphere, no water, certainly no life, just bare rock and metal forged in the heart of a dying star. What's truly revolutionary about these pulsar planets is how they challenge our understanding of planet formation. In normal systems, worlds grow gently from cold dust and gas swirling around young stars. But here, the process must have been brutal and fast, a frenzied assembly in the aftermath of destruction, where molten droplets of heavy elements clumped together in months rather than millions of years. Some theories suggest the pulsar's gravity shredded a companion star, with the remains forming a compact disk that birthed planets. Others propose the supernova's shockwave compressed nearby gas clouds into ready-made proto-worlds. The discovery of these planets in 1992 was a wake-up call for astronomy. Before then, no one imagined planets could orbit something as lethal as a neutron star. Their existence hints that planetary systems might be far more resilient and adaptable than we thought. If worlds can form in the aftermath of stellar Armageddon, they might thrive in other extreme environments too, around black holes, in globular clusters, or even floating freely between galaxies. Yet these pulsar worlds are more than scientific curiosities, they're time capsules from a dying star's final moments. The heavy elements in their composition, like gold and uranium, were likely forged in the supernova itself, meaning these planets are essentially frozen relics of the explosion that birthed them. Every orbit they complete is a silent testament to the universe's ability to create life, even in the ashes of destruction. New observations suggest Pulsar B 1257+12 might not be alone. Other pulsars, like Pulsar B 1620-26, show tantalizing hints of planetary companions, though confirming them is tricky amid the neutron star's erratic signals. With every discovery, the story grows richer, painting a picture of a cosmos where planets can arise in the unlikeliest of places, even around the universe's most lethal lighthouses. These pulsar planets force us to rethink not just how worlds form, but where we might find them. If they can exist here in the radiation-blasted precincts of a neutron star, then perhaps the universe is even stranger and more inventive than we ever dared to dream. Neutron stars might hold the key to one of physics' greatest unsolved mysteries, unifying Einstein's theory of gravity with the bizarre rules of quantum mechanics. For decades, these two pillars of modern science have stubbornly refused to merge, creating a rift in our understanding of reality itself. General relativity beautifully describes the cosmos on grand scales, from orbiting planets to colliding galaxies, while quantum mechanics governs the subatomic realm with uncanny precision. But in the crushing core of a neutron star, where a universe's worth of mass is squeezed into a space smaller than a city, these two theories collide violently. Here, gravity isn't just strong, it operates at scales so tiny that quantum effects can't be ignored, creating conditions unlike anything else in the known universe. This cosmic paradox makes neutron stars the ultimate testing grounds for theories of quantum gravity. Imagine matter compressed so densely that the very fabric of space-time begins to fray, revealing hints of its underlying quantum structure. Some models suggest that at these extremes, space itself might become granular, composed of indivisible units far smaller than atoms, a foam-like sea of fluctuating dimensions where traditional notions of distance and time break down. Others propose that neutron star cores harbor exotic states of matter where gravity becomes entangled with quantum forces, allowing particles to communicate across apparent voids in ways that defy classical physics. The stakes couldn't be higher. If observations from neutron stars match predictions from quantum gravity theories like loop quantum gravity or string theory, it would revolutionize our understanding of the universe. Already, gravitational wave detectors like LIGO and Virgo are scrutinizing neutron star collisions for anomalies in their signals that might betray quantum spacetime effects. Even tiny deviations from Einstein's predictions in how these stars warp space-time during mergers could point toward new physics. Meanwhile, X-ray telescopes study pulsar glitches and oscillations for patterns that might reveal quantum behavior in their superfluid cores or crusts. What makes this pursuit so thrilling is its potential to answer existential questions. Are space and time truly fundamental, or do they emerge from deeper quantum interactions? Can gravity itself be quantized like the other fundamental forces? Neutron stars, with their impossible densities and magnetic fields, might be the only objects in the universe where these questions can be tested experimentally. Every pulse, every gravitational ripple they emit carries encrypted messages about the nature of reality, messages we're only now learning how to decode. Unlike Earth-bound particle colliders, which can't recreate the sustained crushing pressures inside neutron stars, these cosmic laboratories operate around the clock, pushing matter to its breaking point. Some theories even suggest their cores might contain microscopic black holes or cosmic strings, hypothetical remnants of the early universe that could serve as Rosetta Stones for quantum gravity. As we gather more data from missions like NASA NICER and ESA's Athena, each observation chips away at the barrier between the very large and the very small, inching us closer to a theory that might finally unite them. In the end, neutron stars aren't just relics of stellar death or exotic curiosities, they're bridges between two seemingly irreconcilable worlds. By studying how they bend space, warp time, and challenge the limits of matter, we're not just exploring distant objects, we're probing the deepest layers of existence where the answers to physics' greatest puzzles may be waiting, locked in the heart of a spinning stellar corpse. From the unimaginable density of their cores to the mind-bending extremes of their gravity and magnetism, neutron stars have shattered every expectation we ever had about how matter behaves. We've explored 30 astonishing facts that reveal just how strange these cosmic survivors truly are, how a single teaspoon of their material would weigh as much as Mount Everest, how their magnetic fields could strip atoms apart from thousands of kilometers away, and how their collisions forge the very gold in our jewelry. These aren't just dead stars, they're natural laboratories where the laws of physics are pushed to breaking point. Think about what we've uncovered. Neutron stars spin faster than blender blades, warp light into perfect rings, and vibrate like cosmic bells with vibrations so precise they ripple space-time itself. Some blast gamma-ray flares strong enough to affect Earth from halfway across the galaxy, while others lurk in the darkness, their surfaces dotted with mountains just millimeters tall yet heavier than entire mountain ranges. They rewrite the rules of matter, turning atomic nuclei into bizarre quantum soups, crystallizing into cosmic diamonds, and possibly even hiding cores made of free-floating quarks. Every discovery peels back another layer, revealing just how much we still don't understand about the universe's most extreme physics. But here's the most thrilling part, we're only scratching the surface. Each neutron star is a puzzle box wrapped in layers of mystery, from the unexplained glitches in their spins to the way their magnetic fields somehow persist for millennia. They challenge us to rethink everything we know about gravity, quantum mechanics, and the very fabric of reality. And with every new telescope, every gravitational wave detection, we get closer to unlocking their secrets. So the next time you look up at the night sky, remember, hidden in that vast darkness are these tiny but mighty remnants of stellar explosions, whispering clues about the universe's wildest extremes. They remind us that curiosity is our greatest tool, that there's always more to discover just beyond the edge of what we know. Stay fascinated, keep questioning, and who knows, maybe one day you'll be the one to unravel the next great cosmic mystery. The universe is waiting.